Okay, let's talk about chapter 5, singularities. Singularities. Okay, so in the singularity part, we're going to talk the bad point. Bad point means it's not analytic, right? It's not analytic. Um, the first section, let's see the classification of singularity. Okay, so first let's see the definition, and then we have a little discussion. A function f has an isolated singularity. Isolated singularity at z equal to a if there is r, capital R greater than 0, such that f is defined and analytic in the bone centered at A with radius r, but we remove the center A. It's called the punctured disk. A punctured open disk. Okay, so a punctured open disk. All right, it's defined and analytic in a punctured disk, but not in the open disk. So basically, we just say it's not analytic at point A. All right, so this is a so-called isolated singularity. And this point A is called a removable singularity. A removable singularity. If so, it's isolated, and then we talk about the removable singularity. The point A is called a removable singularity if there is an analytic function G from this open disk to C such that G of A as G of Z is equal to F of Z for every Z from this punctured open disk. So if you can have a good analytic function which can recover this F, and also you see here, A is in the definition of this better analytic function, then we say A is going to be removable. So removable singularity must be an isolated singularity. Okay, so this point means the point from here. So we first define isolated singularity, and we continue this classification or the definition sequence. It is called removable if you can extend the analytic function to the point. All right. So we will see that this. We will see, not at this moment. We'll see the sine z over z, 1 over z, e to 1 over z, all have isolated singularity at z equal to 0, because here z all appear in the denominator, so z cannot be 0. So from the definition, they have singular point, isolated singularity at 0. And only sine z over z has a removable singularity at z equal to 0. So they all have isolated one, but just the sine z over z has removable one. These two are not removable singularity, which means you cannot extend the function to z equal to 0. Right? So that's the remark so far. Here, this is clear, and why this is removable, we will prove. We'll prove why it is removable. And let's see why it is removable. There is a very, very effective theorem. The theorem is the following, 1.2. So if f has an isolated singularity at A, then the point z equal to A is a removable singularity if and only if, okay, what condition? This condition is very neat. Limit z approaching A, z minus A times f of z equal to 0. This is an equivalent characterization. It's not just sufficient, it's equivalent characterization. Okay, so if we prove this, we will see that sine z over z, A is equal to 0 in this case. So before we prove it, let's see here. You cancel z and you will have sine z. We know sine z is continuous function at 0. The limit is 0. So here it will imply z equal to 0 is removable. Right? So this is a very, very fast computation which can tell us the singularity is removable or not in many cases. Okay, now let's see how do we prove it. Also, we will see here, this one is not removable. You see. It is not removable. Oh, sorry. It's 1, not equal to 0, so it's not removable. Correct? Another remark before the theorem. Isolated singularity. We know that all the zeros, if you have a non-zero analytic functions, all the zeros are isolated. But here, we specifically mention this is isolated singularity. It means there's some other singularity which is not isolated. For example, if we have 1 over sine of 1 over z, sine of 1 over z, let's check. 1 over z is 2n pi sine 2k pi, n pi or 2n pi, or let's use n pi. 1 over z is equal to n pi. Sine 1 over z is going to be, no, this is always good. Tangent. Tangent of 1 over z. We know tangent function is not defined at n pi plus pi over 2. Tangent function is not defined at n pi plus pi over 2. That's a vertical asymptote, right? So 1 over z is equal to n pi plus pi over 2. Tangent function is undefined. And so it tells us z equal to 1 over n pi plus pi over 2 is a singular point. Singularity for n belong to all the integers or natural numbers. And you can see that the sequence converges to 0 as n approaches infinity. Right? When n approaches infinity, this converges to 0. So 0 is not an isolated singularity. Correct? 0 is not isolated singularity for tangent of 1 over z. So you have a sequence of a singularity point converge to 0. Any of them is a isolated singularity. Each 1 over n pi plus pi over 2 is isolated, but 0 is not. 0 is not. Okay. So this is one example. It contains a non-isolated singularity. Another example is that natural log. Natural log, how do we define the natural log? We remove the negative real axis, including the origin. That's a domain. Then has non-isolated singularities at all negative real numbers. Every point from this negative real axis, including 0, and 0, including any point here. You draw a circle, you draw a disk. There's always a segment in the disk, so that the function is not analytic. So there's no analyticity over the punctured disk, right? So in this example, it has a continuous curve. Here you just have a point and a convergent sequence. They're slightly different. Okay, so these two examples give us non-isolated singularity, which we do not discuss so far. And these two examples give us the application of a theorem 1.2, how to determine the removable singularity. Now let's prove 1.2. Let's prove 1.2. The proof. Okay, so suppose F is analytic in this punctured open disk. Okay, it's analytic in the punctured open disk, and we define the extension. We define g of z, but not the extension of f. We define the extension g of z is equal to f of z if z belongs to this punctured open disk. Z minus a. It's a z minus a times f of z, defined like this. And if z is equal to a, we define to be 0. Right? Defined to be 0. It's a z minus a times f of z is equal to g of z. And at a it is equal to 0. Okay. Then from here we can see that G is continuous in this open disk. G is continuous in this open disk because the limit, when z approaches a, the limit is 0, so it's continuous, at least. Outside a is analytic, but so far I don't know. I don't need that part. All right, so we have a continuous open disk, continuous function in the open disk. And we will show that G is analytic in the open disk. We're going to show it is analytic in the open disk. Well, from the continuity, how can we show it is analytic? We're going to use Morera theorem. Okay, we're going to use Morera theorem. Well, if we already show it is, okay, so later we will apply Morera theorem to get the analyticity. Now let's see, assume if G is analytic in BAR, then what? Then G of A equal to 0 implies G of Z is equal to Z minus A times H of Z, where H from this open disk to C is analytic. Right? We know that whenever you have a 0, you can factor out a factor Z minus A. And from here we see that H of Z is equal to F of Z if Z minus A is between 0 and R. Why? Because they are equal, right? And when Z minus A is not equal to 0, you just directly cancel them. You directly cancel these two things when it is not equal to 0. So they equal to each other, and H of Z is defined and analytic at A. H is defined over the whole open disk. So this satisfies the definition of a removable singularity. All right. So if we prove G is analytic, then we are done. We don't find the extension of F directly. We find the extension of Z minus A times F. We find the extension Z minus A times F. Okay. Okay. Now let's apply Morera theorem to show G is analytic. Morera theorem. Check here. We have open disk, so it's a region. So let T be a triangle in this BAR, in this BAR, and let delta be the inside of T. Where is T? So basically, we just have the triangle and include with the interior part. Okay, the similar stuff we did it last time. Okay, now let's see. A is here. So case 1. Case 1, your triangle is like this. Your delta is here. Case 1, A does not belong to this delta, not inside, not on the boundary. if this happens, remember we have some concept called homotopy. Then t can shrink to a point. So t is homotopic to 0 in this punctured open disk. It's in the punctured open disk. It's always contractible inside the disk. But we emphasize this homotopy does not pass through the center. The center looks like a bad point so far. All right. So since it's homotopic to 0, and G is analytic this part, so integral of G over T is equal to 0 by Cauchy's theorem. So this part we use the analyticity of G in the punctured open disk. All right. Okay, so this is a case 1 and case 2. Case 2. We have A as a vertex. A as a vertex of the triangle. This is A. And B and C. T is equal to A, B, C, A. A, B, C, A. All right? A, B, C, A. When this happens, we choose an X from segment AB and choose an Y from segment AC. Choose X in segment AB and Y in segment AC and connect them. Connect them, we have T prime, which is A, X, Y, A, and T double prime as X, B, C, Y, X. X, B, C, Y, X. You see here in this 1, 2, 3, 4 quadrilateral, it is the orientation is from Y to X. In the triangle, the orientation is from X to Y. Okay? Different. It's bad to draw this small. So you see X, Y. Here is a Y, X. They have opposite orientation. So the integral of G, integral of G along T is equal to integral of G along T prime plus integral of G along T double prime. Right? One is from prime, one is from double prime. And T double prime is homotopic to 0 in the punctured open disk. Right? This quadrilateral. And G, of course, is analytic, so this part is 0. This part of integral is 0 by the Cauchy's theorem, again by the Cauchy theorem. So what we get? We get the integral of G along T is equal to the integral of G along T prime. The big one is T, the small one is a T prime. And we know the length of T prime is less than or equal to the length of T. All right. Okay, now let's see what we can get. G of A is 0. G is continuous. So there, for any epsilon greater than 0, there is a delta greater than 0 such that such that what? Such that the absolute value of g of z is going to be less than or equal to epsilon over L over t for z minus a less than delta. Of course, we require this delta less than r. We require the delta less than r. We need small enough. Okay. And we can choose x and y close enough. Here, x and y are arbitrary points from AB and AC. So we can choose x, y close enough, close enough such that the whole small rectangle is totally contained in BA delta. BA delta, so the whole thing is contained in the smaller delta. Then what we get? We check this. The integral of g along t absolute value is equal to the integral of g along t prime. And it's less than or equal to the integral t prime absolute value of g. Gz is less than epsilon over L of t, so it's less than integral epsilon over L of t dz t prime here. And this one is equal to epsilon L of t prime over L of t. This is less than epsilon. All right, so you see, we use a smaller, we basically, we have, originally we may have a very huge triangle, which is cut, make it smaller, and we remove the additional part. This additional part does not contribute to in the integration. This additional part has integral always 0. So the length of this smaller rectangle triangle is clearly less than the length of a bigger triangle. All right. Okay, good. So we get absolute value of an integral of g along t is always less than epsilon for arbitrary epsilon. Hence, this integral is equal to 0. Okay, this is in case 2 is equal to 0. Case 3. Case 3, the A is not the vertex. A can be a boundary point. So for example, we have, let's make it bigger. A, like this. If this happens, C, D, we just connect the A and the C. We will divide this triangle into 2 parts. Right? So T is equal to D, A, B, C, D. And connect A and C. We have 2 triangles. Triangles. T1, A, B, C, A, and T2, A, C, D, A. See, CA from C to A, AC from A to C. They will be cancelled eventually. We have 2 triangles with this, and we apply case 2, because in both triangles, the integral, point A is a vertex of each triangle. So we can apply case 2. We have this both those two integrals along these two small triangles is equal to 0. Hence, this integral is equal to the sum of them, so it's equal to 0, right? And case 4. Case 4, A belongs to delta, but A does not belong to T. It's inside. Inside, actually, it's similar to this. This part, we divided the triangle into two pieces. If it's inside, we will B, C, D, A. We will connect A, B, A, C, A, D, and we will have 3 triangles, and all 3 triangles satisfy the case 2, and we get it. So we apply case 2, we have the same result. So eventually we see that all applying collecting all 4 cases, we see that the integral of G along T is equal to 0 for any or for all triangular paths T. So we apply the Moreira theorem, we get G's analytic. From G's analytic, we get the H is equal to F. Correct? So that's the proof, the complete proof. Of course, if you have, this is a proof from limit go to the analyticity, but the other one is trivial, right? If G is, if F is, what is the other one? Yeah. If F has a removable singularity at z equal to A, then there is an analytic function G. There's an analytic function G such that GF satisfy the definition. GF satisfy the definition of a removable singularity. And then we compute the limit z approach A, z minus A times f of z. Remember, for this limit, this z is not equal to A. If z is not equal to A, you can replace f by g of z. And now we are going to use continuity, because this one is a continuous function, this one is a continuous function, so you can apply the continuity. Z minus A is A minus A times g of A. G of A, whatever, but A minus A is 0, so this is 0. Okay, so this part, Z is not equal to A. But this part, we're going to use the continuity of Z minus A and G of Z. This part we don't know if F is continuous at A or not. So that's why we must pass from F to the better analytic function G. All right. So now we get a complete classification about complete characterization about the removable singularity. We just check that Z minus A times Fz. Okay, so that's the characterization of a removable singularity. In the real calculus, we see that this function f of z is not differentiable at x equal to 0, but continuous. And of course, it's a singularity. So if you check that x minus 0 times upper value of x, and you let x approach 0, this is definitely 0 because both functions are continuous. So for the real calculus, this condition is not equivalent to the removable singularity. All right, so it is actually just singularity for the differentiability, not singularity for the continuity. But the characterization we just proved to show that this situation, the theorem above shows that this corner situation will not happen in complex analysis. In complex analysis, we don't have corners. Once you have a corner, it will be round. Only the real analysis will have a corner, the bad point for the differentiability. Okay, removable. Still, even though from the first look it's not analytic, but we can just overcome it. Removable just means we can overcome it. So in the textbook it says honest singularity. Honest just means non-removable. Non-removable. Honest singularity means that the function f of z will become either infinity at z equal to a, or not at, near, or it does not have any limit. Okay, it does not have any limit. Okay, becomes infinite just means upper value. Okay. All right, because of this observation, let's give the further definition. The definition, if z equal to a is an isolated singularity of f, isolated singularity of f, then a is a pole of f. A is a pole of f if the limit z approach a, upper value of f of z will be infinite. Okay. Well, this upper value is infinite. Just means it becomes very big, larger and larger when z approaches a, closer and closer to a. So that is for any m. So this is an epsilon delta definition. So epsilon capital M definition. There is a capital M greater than 0. For any capital M greater than 0, there is a number epsilon such that ops value of f of z will be greater than or equal to capital M whenever z is sufficiently close to a. Z minus a ops value between 0 and epsilon. Okay, so that's the case when ops value of f of z becomes infinity. This is a pole. It's called a pole if it goes to infinity. If an isolated singularity is neither a pole or nor a removable singularity, it is called an essential singularity. Essential singularity. Okay? It's not a pole, not removable, it's called essential. So we have three types of singularity: removable, pole, essential. Removable, pole, and essential. Okay? So you can easily see that 1 over z has a pole at z equal to 0. 1 over z has a pole at z equal to 0. Well, let's see. E to 1 over z. For e to 1 over z, let's check it. Of course, 0 is a singularity. It's isolated singularity. Let's check it. We compute the limit z times e to 1 over z. It's I'm trying to apply the L'Hopital's rule, but 1 over z is not good. So I'm trying to change. When z approaches infinity, 1 over z will approach infinity. When z approaches 0, 1 over z approaches infinity. I'm going to choose w equal to 1 over z. So it becomes e to w over w, and apply L'Hopital's rule. Right? And clearly this one has no definition. Right? This one has no definition. So it's not equal to 0. Has no limit. For real numbers, it's 0. Has no limit. It's not equal to 0. So 0 is not removable. 0 is not removable. Let's check the other one. Let's check the modulus of 1 over z. Modulus of 1 over z. Z, let's call it, z is rei theta. So 1 over z is 1 over e to negative I theta. So it's 1 over r cosine theta minus I sine theta. So it's 1 over r cosine theta minus I 1 over r sine theta. Remember, e to x plus iy is e to x times cosine y plus I sine y. So this is x, this is iy. So it's e to r 1 over r cosine theta times cosine negative 1 over r sine theta plus I sine negative 1 over r sine theta. All right, a little bit tight. Okay, so if you put ops value, you will get E 1 over R cosine theta. E1 over R cosine theta. Then this one, it's not approach 0. If theta, for example, if here theta, we constantly choose theta, what is a theta? Theta is pi over 2. If theta is pi over 2, this is constantly 0, right? Cosine pi over 2 is equal to 0. Then is 1. If theta is not pi over 2, theta is pi over 2 or 2 pi plus negative pi over 2, there's many. I just choose one case. If theta is 0, cosine 0 is 1. Cosine 0 is 1, you will get e to 1 over r. R approaches 0. R approaches 0. Then this is approaching infinity, this approaches infinity. But anyway, when theta is a pi over 2, you already get a 1. Here you get a 0, so the limit z approaching infinity, ops value e to 1 over z is not infinity. Because in one ray it's not infinite, so it's not always infinite. So this tells us 0 is not a pole. 0 is not removable. 0 is not a pole. Hence, 0 is an essential singularity. Zero is an essential singularity. Okay, so that's what the textbook mentioned. It's not difficult to see that although z equal to 0 is an isolated singularity, but exponential, this one is essential. So you have to consider it's not removable, it's not a pole, then it will be solved. All right, so so far we gave the definition of 3 types of isolated singularity: removable, pole, and essential. And we also have the corresponding examples. So we have 1 over z is has a pole at 0. E to 1 over z has essential singularity, and sine z over z has a removable singularity. And we also gave example about the non-isolated singularity, the tangent 1 over z and natural log of z. All right? So later we will continue the discussion and see more characterizations about different types of isolated singularities. We will have more discussions later in the future video. Okay, thank you very much, and we finish.